This is experiment number 2, shaded. So what you'll do is read the temperature on the 2 thermometers before you put them down. Record that. Put one in the sun, one in the shade, and then you're going to leave them for 20 minutes. So you can go and do the other experiment for week 1. But then also you can discuss what they anticipate happening as far as the temperature. So you can have the discussion as well. And then read the temperatures and record them, and you can discuss the difference in temperature, do the math. Yeah. This is number 17, same place, and we're going to determine why satellites appear to be stationary. How come when we look up at them they look like they're not moving when obviously we know that they are? So they're going to stand facing each other. Peter is by our pretend tree, which is a pole because I don't have a tree in the middle of the yard. And they're going to walk around. He has to stay with his back to the tree, kind of almost sliding around. I don't know what the word is. And then Ben can walk more straight, but we're going to give it a try. So go ahead. Peter, move slowly, slowly. Hey, Peter, slow down. Oh, wow. Look at how fast Ben has to go to keep up. Keep going. Keep going around the tree. Ben, you're not facing him. You got to go faster. Faster, faster, faster. Straighten your rope out. Straighten your rope. All right, so we can see what's happening, that Ben has to move a lot farther, so he has to go faster to keep up with how fast the Earth is moving, how fast the Earth is spinning. This is week 2, experiment number 24, Mirage. And so we have our materials. We have modeling clay, a small bowl you can see through, a coin, a helper, and a pitcher of water. So we're going to take the ball of clay, we're going to stick it in the bottom of the bowl, and then we're going to take our coin, we're going to put that on top and get that to stick. And then we're gonna watch it while we do it, I guess. So it says to stand near the table so that you can see the whole coin, but then you're gonna back up slowly until the coin is just barely out of sight. Okay, and then we're gonna, but now we have to, I'll pour the water. So now we're gonna pour the water. How far? I guess we're gonna fill it. Now we're gonna watch it again. I don't think I'm gonna be able to show this on my camera.
Stop. And come over here.
All right, so we are on number 26, distortion. We're going to determine how the atmosphere affects the viewed shape of the sun. So our materials are a pencil, a white sheet of paper. It says in the directions to use a compass, but we're just going to trace our quarter from the last experiment, and then a magnifying glass. So go ahead, Peter, can you trace that? For the younger classes, the parents will have to do this part of it. But you know, the medium and up can probably do it themselves. And then he's going to take the magnifying glass and hold it right up against it and look at what happens when he moves the magnifying glass back and forth. Is it changing, Peter?
Yes.
How's it changing?
Gets bigger.
It gets bigger? Does it change shape so it's no longer really a circle?
Yes.
Yeah. So maybe it gets stretched out or more like an oval. And that is because of refraction. That's how it's getting distorted. So you can hold your magnifying glass that way. Just let them experiment while you lead the discussion. This is number 9, see-through, and the purpose is to determine how Saturn can be seen through its rings. How come the rings don't get in the way when we're looking at Saturn? How come we don't see them? So the materials are a ruler, Sharpie, a card, a 3x6 card, which I've cut out, scissors, a straight pen, pencil, and glue stick. So the first thing we want to do is draw the lines on it, and we can use, we'll just use the edge of the ruler. We'll just line it up and do it that way. Yeah, so we'll do the first line with the ruler lined up, and then we will kind of cut that in half and do the other line. Good. And then you'll want to cut these into 3 sections. So obviously the younger classes will probably have the teachers or the tutor or the parents help. And then the next step is to glue them together right in the middle. It's not like they have to be glued super strong, do they? As well as you can, I guess. The glue stuff. So yeah, start 90-degree angles. And then we'll go the other way. And then this next part we'll have to have, for the younger kids especially, we'll have to have the parents help. We're going to take our pin and stick it through the middle of it. And then we're going to stick all of that into the eraser tip. Well, it doesn't look like it has to go in that far. And then we're going to spin it. Is that right? Yeah, spin it. Yeah, that's good. So and then they can observe what happens, and it starts to make it so you can see right through it. Like I can still see what's going on in the back of it, even though there's rings in the front of it because we're spinning. Okay, so this is number 11 on the move, and the purpose is to determine why planets continue to move. So our materials are the round cake pan, pencil, sheet of construction paper, scissors, and a marble. So we're going to trace a circle on the paper, and then cut out the circle. So this will just be a demonstration when the whole class goes together. Put it back in the cake pan, and then we're going to take the marble and thump it. I would say bump. There we go. So that starts rolling around the pan. So, and then you're supposed to notice what happens with that, which it didn't keep going. That's what I noticed. And then we're going to take it out, do the same thing without the paper, and see what happens. And it goes a lot longer, that's for sure, without slowing down. So the question is why? Why does it go longer without the construction paper? And the keywords are inertia, friction. So talk about that. Okay, so this is experiment number 12, Speedy. And what we've done, can you hold it up, Ben, so they can see? What we've done is we've taken our yard-long piece of string and we've attached a metal washer to the end of it. So Ben's going to hold the end of the string. He's going to stick his arm straight out in front of him. And then he's going to spin it. There you go. And he's going to see how fast he has to go. Don't go faster than you have to, but he's going to go as fast as he has to keep it taut or straight. Okay, and then he's going to stop and he's going to hold it halfway, right in the middle. And he's going to do the same thing. And then he's going to hold it really close. He's going to, oh, it got kind of tangled up. You might want to hold on to the end when you're doing it. He's going to, yeah, that's close enough. Well, maybe not quite that close. Back up a little, go a little bit higher. Yeah, there you go. He's going to hold it. Wait, you got to stick your hand in front of you. Okay, now go. You got to go up and down though. Does it work? Oh, there we go. There. Is it getting tangled?
Yeah.
But you're having, stop, I need to talk to you. You're having to go faster the closer you got to the washer?
Yeah.
Okay. So it has to do with, basically it has to do with the sun and how far away the planet is and what that does to the gravitational pull. So we can discuss it. Thanks, Benny.
Please don't.
Okay, this is experiment number 13, and Sam is going to start inflating our balloon just as large as an apple. So he's going to stop right there, and then Noah is going to draw about 20 dots on the balloon randomly. Probably more on the front of it than on the top of it. Yeah. He's going to draw 20 dots on there. This is expanding, so it has to do with demonstrating how galaxies might be moving. So they'll do this with a partner, which obviously will make it a little hard for the person blowing up the balloon to see it, but if they can't see it on their own balloon, you know, they can pull it away and keep it closed and see what's happening the other way. Okay, he's being very precise with the number 20.
Well, you said 20.
I did say 20.
Okay. That was 20.
Okay, so now he's going to blow it up all the way, and the partner is going to watch. Turn and face your partner, Sam. And then you guys are going to decide what's happening. Okay. That's probably big enough. Noah, what's happening?
It's getting fainter but bigger.
Are the dots themselves getting bigger?
No, but
Well, yeah, they are.
fainter.
They're getting bigger.
Well, they're moving with the balloon, so.
So they're spreading out, but the dots are also getting bigger too, right? Can you shrink it again so we can see?
It's getting bigger.
That's how
but-
small they were, and then they got a lot bigger, right?
Yes. But the ink is.
It's getting lighter because it's
Yes.
spreading out. That's right. Okay, say goodbye.
Bye.
Okay, so to set up number 16, you take your masking tape and you tie your string to it, and then you thread it through your spool, and then you tie it to the spoon, and you have to tie it really tight so the spoon doesn't go flying off and hit somebody. And then we're going to go outside and demonstrate. Okay, so you want to hold it, make this distance fairly short when you do it. And then start by holding both, the masking tape, hold it down here, and then we'll let go in a sec. Is that working?
Yeah.
This is week 6, experiment number 3, cover up. So I have my desk lamp, and using that to represent the sun, we're going to determine why Mercury does not create an eclipse. Mercury, of course, being the planet closest to the sun. So you'll want to have students try this one at a time and then discuss their observations and, ask questions, scientific method type questions, and facilitate the conversation. So you want to be 2 meters away from your light, which you can eyeball, and then take your thumb, which represents Mercury, and right in front of your sun, the lamp, and then see how big it is. Oh, it's awfully small. And then you're going to pull it closer and closer to your eye, and now it's blocking my sun completely. So that's the point, is Mercury is so close to the sun that it doesn't cover up much of the light at all, which is why it doesn't eclipse the sun. This is number 4, thick, and the purpose is to determine why Venus's atmosphere is so hard to see through. So for this experiment, it's more of a demonstration, so you'll just do one in class and then the kids can take turns messing around with it. So you're going to stand 2 yards apart, and then the tutor, I suppose in the older classes one of the students could do it. It's going to turn on the flashlight, and the student is going to observe the light. Peter, what's the light like?
Bright.
It's bright, okay. And he's, you can have a conversation about the light, and then you're going to hold the sheet of wax or parchment paper up in front of your face, and now look at the light. Can you see it?
Oh.
Huh?
No.
Not at all?
A little bit.
A little bit. How does it compare to without the parchment? You can take it up and down if you need to look. So there's that, and I put it up. How does it compare?
It's white. The white is way brighter.
It's what?
It's brighter.
It's brighter when it's down. So now put it up again. Is it harder to see?
Yeah.
Yeah? Okay. So you can have a conversation about atmosphere and clouds and what else? Visibility. Thank you. So this is from Peter's angle. That's an awfully bright light. Now he's going to hold this up. Oh, it is kind of hard to see. I think if the lights are off in the room, that would help. I think that'll make it better. It'll make it easier to see what's going on. Okay, so this is experiment 161, spoon bell. And what we did is we took a metal spoon and we took a 30-inch long kite string and we tied it in the middle of the string to the spoon. So it's right in the middle. And Peter is going to demonstrate. So you can stand up, Peter. He's going to take this device that we made. Do you want to stand over here? You can come over here. And he's going to put it up to his ears, the 2 sides, and he's going to gently tap it on the table and listen for what he hears. Okay, good. So you'll want to give each child a chance to try it and to see what happens. Try it if they hit it just a little bit. Try it if they do it more firmly, and get into a conversation about vibration and amplitude and sound waves and yeah. Did it sound different?
Yep.
Yep. This is number 162, humming glass, and we're going to show how friction can cause a glass to vibrate. So it says in the instructions to wash your glass with dishwashing liquid and wash your hands, but as long as the glass is clean in the morning, we should be fine. So you're going to put the glass on the table and you're going to pour, oh, I didn't say my materials. Vinegar, a bowl, and a glass, and your finger. So this is a demonstration. So you're going to pour just a really little bit of the vinegar in the bowl, and then you're going to dip your finger in the bowl, and you're going to rub it, they say gently, but it has to be pretty firmly. There you have it. So it has to do with the friction between your skin and the glass, which is why you need to use the vinegar, because it dissolves the oil. And then when you rub it around, it causes vibration. And then the vibration, you can get into the pitch and frequency and all that stuff. This is number 165, Cold Foot. And so we put our carpet square and our square of aluminum foil. We've had it on the floor for well over 10 minutes, so it's acclimated to the room temperature. Probably have to do this outside because it's supposed to be on tile. I don't think it'll work on carpeting. And then Peter is going to step onto them. Do they feel, what's the temperature? Like, do they feel the same temperature or does one feel colder? You can talk. Look at me and talk.
The tin foil.
The tin foil what?
The tin foil is colder.
The tin foil is colder than the carpet, right? So it has to do with whether or not it's a heat conductor and whether or not the energy is being transferred. Say thank you.
Thank you.
This is number 171, Pepper Run, and we're going to show how we can make black pepper run across a bowl of water when soap is added. So our materials are a bowl of water, pepper, dish soap in a little bowl, just it doesn't take much, and a toothpick. So first we're going to sprinkle the pepper in the bowl, and observe what's happening, that it's floating, it's all pretty much evenly spaced. It's kind of hard to see. And then we're going to take the toothpick, get just a little bit on there, and then we're going to put it in and observe what happens. There, so you can see that. All the pepper looks like every time you poke it, it kind of spreads out and goes to the edges. And that is because
There's a tug of war going on between the soap molecule or the detergent molecule and the water molecules. First of all, the water molecules were attracted to each other and kept the pepper afloat. And then as soon as you introduce the detergent, it has an end that's attracted to the water molecule, and it'll push the pepper away. It's a stronger attraction.
there you have it. This is number 164, bottle organ, and we're demonstrating how frequency affects the pitch of sound. So our materials are 6 small mouth bottles of comparable size, a metal spoon, and some tap water. So we've already put the water in at different levels. So you want to put it and then have a conversation about how this is going to affect it. Talking about things like how it affects the frequency, what the pitch is, stuff like that. So Ben, why don't you go ahead and try it. That's good. Can you try tapping on one at a time? Want to play a song? Mary had a little one. Thank you. So this is number 189, shape up. And what we're going to do is determine how shape has an effect on speed. So our materials are a roll of masking tape, 2 jar lids I taped together with masking tape, and a marble. And I've propped up the table. Can you see it? I've propped up the table with books. So it's at an angle, and so they're going to line them up, and when I say go, they're going to roll down the slope. And what we're looking for, the discussion will involve what is the shape, what is if it has a circle in the middle, center of gravity, things like that. So hold on, guys. On your mark, whoop, get set, go.
Peter cheated. Why?
So this is 190 breakthrough, and we're going to demonstrate how the shape of an object affects its falling speed. So our supplies are 2 sheets of typing paper, a pencil, a compass, scissors, and tape. And it says a ruler, but our ruler is on our compass, so we're good. So what we're going to do first is we're going to make our paper circles. They're supposed to be 8 inches in diameter. There's options for how you want to do this, depending upon, go ahead, why don't you go ahead and make your circle. If you want to do it, based on how much time it'll take, based on the age of your class, you could do them and cut them ahead of time. You could, make copies of the circles and the students could cut them. You could have the kids use the compasses, they could do it all themselves. And then you cut it out after you make it. Make sure you make the dot in the middle, which I think usually well, I don't know if that always happens with the compass. So make sure you put a dot in the middle because we're going to need that. And then she's cutting out, both sheets at the same time. Okay. And then on one of them, you're going to cut, well, I suppose the one with the dot, you're going to cut a straight line going from the outside right into the middle, into that dot. And then you're going to fold it into a cone. And it's not really clear like how tight of a cone to do. So do what you think, and then you could also test it a few different ways, making a tighter cone or a looser cone. And then the piece of tape is supposed to be, 1 inch, a 1 inch piece of tape. And so you'll tape the cone, but then you also have to put a piece of tape on just the plain old circle because otherwise it would affect the weight. Mm-hmm. Okay, so our model is going to hold them, but he's going to hold them at the same height. I don't think those are at the same, okay. And then he's going to let go. We're going to see which one falls faster. Go ahead. Sorry, I couldn't really see. Which one fell faster?
The cone.
The cone fell faster. So then we have a big discussion about why the cone fell faster. All right, so this is number 174, energy change. And our purpose is to demonstrate the effect that height has on the energy of a moving object. So our supplies are a cup with a 1.5 inch square section cut out of it. And so I'm giving you the cup already pre-cut. And then a ruler, a pencil, a marble, and a book. Okay? So we're going to start by having the pencil under the ruler, and we're going to take our marble and put it in the groove of the ruler and then let it go. watch what happened. Did the cup move, Peter?
Tiny bit.
Tiny bit. Okay. Now we're going to try it again, but this time he's going to put the book under there. And we'll see what happens. Oops. There we go. He's going to put the marble on the book. Whoa, that moved a lot, didn't it? And then if you wanted to, you could try it with different height books. Just mix up the way you're testing it to analyze what effect does the angle, does the height have on it. And we'll get into potential energy, kinetic energy, and what's happening with that. Thank you very much. What do you say?
Thank you.
This is number 177, SNAP. And we're going to demonstrate that an object remains stationary due to inertia. So our materials are paper cut into a 4 by 10 inch strip, and then a can of soda. So what we're going to do is we're going to put the soda on top of the paper, and we're going to hold, at the end of it, and we're going to hold the paper. We're going to push it close to the can, and then we're going to quickly snap the paper away. And the can didn't move. So the discussion is why? Why didn't it move? What is inertia? Inertia resists changing its motion, and because the can was stationary, it's not going to move even though the paper moved. This is number 184, lifter, and we're going to determine how a screw works. So we're going to put 2 fingernails, or if you can, if you don't have long fingernails, I guess at least 1 fingernail at the tip, and then hold the head of it with your other hand and turn it clockwise. And then as the screw turns, the ridges are going to spiral downward, and the fingers stay in place. But I don't know why I said it that way. So your fingers are not moving, but the screw is moving because you're climbing up the, you're going up. It's like an inclined plane. And then screws actually act like wedges too, where they get in and they kind of pry things apart. That's how you can screw something into wood. This is number 185, ramp, and our purpose is to demonstrate that a winding mountain road is an inclined plane. So to figure out what an inclined plane is actually. So we're going to start with a 5-inch, it's made from a 5-inch square, but it's a triangle now, piece of paper. And we're going to draw color the longest part of the triangle. So they can do this in pairs. And then we're going to tape the triangle to our pencil. Technical difficulties. I just like three pieces of tape. Gotta show us what you're doing. Okay, so now it's taped, and if you hold it upright, there you go, you can wrap it around. Well, before you even do that, you can look at it and you can see that it's a ramp, and it's a pretty steep ramp. And now we're going to wrap it. And now, it was still a ramp, that didn't change, but now it's going around the mountain, and it's not as steep of an angle, so it's easier to go up, but it is longer. So it's a simple machine because a machine makes work easier. So that's an example of an inclined plane.